Turbomachinery Pelton Wheel. In this video, I would like to share with you the analysis of the water jet and the energy head that can we take from the Pelton wheel system. So this is the basic diagram of Pelton wheel. So we have a water dam here. So I draw as a water tank here, and then we have a high water level here, and this water will flow through a pipe system here, and then to increase the velocity, so we have nozzle at this end of this pipe. So the nozzle will increase the velocity, so the water jet that comes out from the nozzle here will have high velocity. So and then the water jet here will hit bucket here. The bucket of Pelton wheel will rotate the wheel, and at the same time the shaft that connected to the wheel here will rotate and rotate the generator here, and then we could produce electricity. And then from here the electricity will go to the transformer, and then the electric will distribute to the national grid line. Normally people will take a hydraulic head as the level from the water level at the dam here to the center point of the nozzle of pipe system here. So however, to calculate the input power of Pelton wheel, effective head is required. So this is the effective head. Because the head of hydraulic here is not equal to the effective head here. The effective head here is the effective head of energy that could give the input power of the Pelton wheel. So if we see the system here, we could find that we have a pipe system from the water level, from the water tank here to the nozzle. And we imagine that the losses in pipe need to be calculated. So normally losses in pipe can be calculated by using equation of this one. You learn about this equation in the fluid mechanics 1. So the major loss in pipe is equal to F L over D V square over 2G. The F here is the Darcy coefficient of friction. So you may take the value of F here, depends on the Reynolds number and from the Moody chart. But sometimes in our examination, we will give you the value of F here. And the V square here, the velocity here is the velocity of water inside this pipe, not the velocity that hit the turbine. So, and it is this velocity didn't have any connection with the velocity triangle at the Pelton wheel. So please be remember, this velocity is the velocity inside this pipe because we are calculating the losses in this pipe. And then when the water flow through the nozzle here, we need to know that the minor loss in nozzle also need to be calculated. Normally, coefficient of nozzle, Cn, will be given. So we could write velocity at nozzle, mean velocity after it go through the nozzle here, velocity at nozzle can be written as Cn times square root of 2gh. And h here is the energy head before entering the nozzle, because we want to calculate the velocity after the nozzle. So we need to know what is the head of energy before it's entering the nozzle, because we will use the previous energy head here, and then we multiply with certain coefficient here. For this case, we call it as the coefficient of nozzle, Cn, to get the velocity after it's go out from the nozzle here. Then the velocity that comes out from the nozzle here can also, it's now heat the blade, and we call this velocity is velocity of jet, because the phenomenon of the nature of this velocity is it travel in atmospheric pressure and it will become a water jet. So we call this velocity is velocity of jet. And you must know that when it's travel openly like this in atmospheric pressure, the velocity at the nozzle here and the velocity that hit the bucket here will slightly reduce, because there is energy losses along this movement. So we could calculate the velocity of jet here is more specifically to mention the velocity of water jet that hit bucket. So we could calculate the velocity of jet that hit bucket by using this equation, CV times square root 2GH. And CV here is the coefficient of velocity, and H here is the energy head at nozzle. The CV here will represent the energy loss of this water jet before it hit bucket. And the energy H here, the energy head, must be taken the energy at the nozzle here. Because we calculate the velocity at the nozzle, we multiply with coefficient of velocity to get the velocity that hit bucket. And then the energy that hit bucket is assumed as the input energy of the Pelton wheel. For example, if we could know the velocity of jet that hit bucket here is 15 millimeter per second, the effective head can be calculated as V square over 2G. So we substitute the value of V here with 15 meter per second. We could get the head of effective here is equal to 11.47 meters. And we could calculate the hydraulic efficiency is rho GQ Euler head divided by rho GQ effective head. And Euler head can be assumed as the energy head after water hit the bucket. So the water will hit the bucket and it's become the effective head, the input power to rotate this Pelton wheel. Then when the water hit the bucket, the wheel rotate and the power just outside, the power that the output power here is Euler head. That's why the hydraulic efficiency can be written as Euler head over effective head. When water jet hit the bucket, it spins the Pelton wheel and it will generate power or electricity. However, friction and other losses that occur in the shaft and other mechanical part here will reduce the power that received by the generator. So we need to calculate the efficiency of the mechanical parts here by calculating power at turbine shaft, mean power at here as the output power, divided by power produced by the wheel. And power produced by the wheel is Euler head. And finally, current flows to the transformers and then distribute to the national grid line. So this is the basic idea of Pelton wheel in common application.